GCE Advanced Level Chemistry Practical Series Experiment number 35, Experimental Determination of Acidic, Basic and Neutral Nature of Aqueous Salt Solutions by testing their pH. So, the aim of this experiment is to take different salts and form aqueous solutions of these salts, and then with the use of a universal pH indicator, we are going to measure their pH value. And based on the pH value, we are going to categorize each of these aqueous solutions as acidic solutions, basic solutions, and neutral solutions. So, the aim of this experiment is to identify the acidic, basic or neutral nature of each of these aqueous solutions that we form here. Now, let's move on to identifying the different reagents we will be using for this experiment. Students, let's take a look at the chemicals we will be using for this experiment. We will be using sodium chloride, which is a very common substance for you, salt that you use when you are cooking, and we have sodium acetate, we have ammonium acetate, ammonium chloride, zinc chloride, aluminium chloride, and magnesium sulfate. Apart from that, we will be using universal indicator solution. We have taken a small amount of our universal indicator into this small beaker here. We will be using a dropper to take small amounts of universal indicator. We have distilled water. We will be using distilled water to make aqueous solutions of each of these compounds that we have here. Apart from that, we will be using small plastic spoons to take each of these solids into these test tubes that we have here. So, we have test tubes to make our solutions. Apart from that, we will be using a measuring cylinder to measure 10 milliliters of water when we are making each of these solutions. So, these are the chemicals and the equipment we will be using for this experiment. Now, students, we are going to be measuring the pH of different aqueous solutions in this experiment, and in order to do so, we are going to take approximately about 0.5 grams of each solid that we have with us, and then we are going to dissolve it in about 5 cubic centimeters of water. And to each of these aqueous salt solutions, we are going to add the same amount of universal indicator. We are going to add a few drops of universal indicator to each of these aqueous salt solutions we have with us. And we are going to make sure that we are adding same amount. We are adding the same amount of the universal indicator to each of these solutions to keep everything or all the factors constant. We are going to make sure we are adding the same amount of universal indicator to each of these aqueous solutions that we prepare. When we are getting started, one of the most important things is the color chart that is given in the back of our universal indicator bottle. As you can see here, students, we have the color chart that is given here. This color chart helps us determine the pH of a given solution. When we add a few drops of universal indicator to a solution, the solution will change color. Because of the presence of universal indicator, it will give out different colors. And based on the color that the solution is giving off, we can actually figure out the pH of that particular solution. So, when it comes to observing these colors, since it is difficult for you to observe these colors that we have over here, we have scanned this label and displayed the same colors on this digital screen that we have here, so that we can very clearly observe these colors. And if you want to properly see the colors, we can move around, we can observe these colors very clearly. Now, we are going to first measure the pH of water. We are going to first measure the pH of water. In order to do that, we are going to take about 5 cubic centimeters of water. We have a measuring cylinder here. We are going to add 5 cubic centimeters of water to this measuring cylinder. And then we are going to transfer 5 cubic centimeters of water into a test tube. And then we have a small amount of universal indicator taken into a small beaker here. You can observe the universal indicator is red in color. And we are going to take a small amount of universal indicator and we are going to add a few drops of the universal indicator into our test tube here. And we are going to mix it really well. As you can see, when we added the universal indicator to water, the indicator was no longer red in color. It changed color, right? So this color will tell us the pH of water. So now let's compare it against the pH chart we have over here. We can see when you are moving all the way from pH 411 that we have here, when we are moving up, we can see the pH of this water is 7. You can see the color that you observe in this test tube is exactly pH 7. It is not pH 6, it's not pH 6.5. It clearly matches with the pH 7 according to this color chart. So students, the distilled water that we have at the lab is having a pH of pH 7. Now students, we have observed the pH of distilled water that we have in our lab. Now let's move on to our first salt. We have sodium chloride. So let's make a small aqueous solution of sodium chloride and then observe the pH of a salt solution. We have our sodium chloride here. We are going to take a very small amount of sodium chloride, approximately 0.5 grams of sodium chloride. And we are going to add this amount into a test tube. As you can see, sodium chloride is a white color solid. I'm fully aware that all of you know this by now. Then we'll measure 5 milliliters of water. And then we'll transfer this 5 milliliters of water into our sodium chloride solid that we have here. Now we have dissolved the sodium chloride that we took into our test tube here. Now we can move on to adding the same amount of universal indicator that we added to our water will be added here as well. So we are going to make sure that we add exactly the same number of drops of universal indicator into the sodium chloride aqueous solution as well. Right, students, let's observe the color of this sodium chloride solution. If you pay close attention, you can see sodium chloride also is having a color that is close to pH 7. So the sodium chloride solution that we prepared had a pH of pH 7. This indicates the sodium chloride solution is a neutral solution. As you know, students, when it comes to room temperature, pH 7 is characterized as a neutral pH. Any pH above the pH 7 indicates that the solution is alkaline or basic. So starting from pH 7 and upwards, 8, 9, 10, 11 indicates that the solution is basic or alkaline. When it comes to pH values below 7, from 7 to 0, it indicates these values are acidic. When you're going below pH 7, pH 6, pH 5, pH 4, and so on, pH values below the value of pH 7 indicates that the solution is acidic. So what we observed for sodium chloride solution was a pH 7. So the pH of sodium chloride was 7, indicating our sodium chloride is a neutral solution. So this is clear to us that sodium chloride had a neutral pH. Now, let's move on to our next solution. Now, we are moving on to sodium acetate. So we have our sodium acetate here. We are going to take a small amount of sodium acetate, dissolve it in 5 cubic centimeters of water, and then we are going to add our universal indicator and observe the color of the solution. And based on the color of the solution, we can determine the pH of the solution. And based on whether the pH is below 7 or above 7, we can determine whether this solution that we prepared is acidic, basic, or neutral. We have a spatula here. We'll take a small amount of ammonium. We'll take a small amount of sodium acetate. About 0.5 grams of sodium acetate can be taken into our test tube here. As you can see, sodium acetate is white color crystalline solid. And then we are going to add 5 cubic centimeters of water. To measure 5 cubic centimeters of water, we can use a measuring cylinder. Now we have measured 5 cubic centimeters of water. Let's add that to our sodium acetate. And let's dissolve the solid. So now we have prepared an aqueous solution of sodium acetate. It's a clear solution. And we are going to add the same amount of universal indicator that we added to both of the previous solutions. We had a little bit of water. We added a few drops of universal indicator to the water sample we took, and then we add the same amount of universal indicator to our sodium chloride sample, and we have here a different salt, sodium acetate. So we are going to add the same amount of universal indicator to this sodium acetate solution as well. Now students, as you can see, when we added our universal indicator, the color of the universal indicator was red, but now we can see the solution is green in color. So the universal indicator has changed its color. Now let's compare it against the color chart that we have here and observe the pH of this particular solution. Now students, as you go down, is it blue or is it light green or is it somewhere in between? Is it light green? Is it dark blue or is it somewhere in between? You can observe that that value is 8.5. So the pH of this solution is 8.5. So students, just to give you a very clear picture, we can see the pH of this solution is 8.5. Sodium acetate has a pH of 8.5. So when you have a pH of 8.5, what does that indicate? It indicates that this solution is basic. Any pH value above the pH of 7 is indicating that the solution is basic. Why was this solution basic? Now you might have learned about the fact that when a strong acid reacts with a weak base, the salt that is formed is going to have acidic properties. And the reverse argument of this is also true, which is when a strong base is reacted with a weak acid, the salt that is formed is going to have basic properties. So sodium acetate is going to be formed as a salt when we react acetic acid or any carboxylic acid for that matter dissociates partially in water and therefore they are weak acids. So when acetic acid reacts with sodium hydroxide, and as we know sodium hydroxide is a strong base, the salt that is formed is sodium acetate. Sodium acetate is going to be a basic salt because it is produced as a result of a reaction between a strong base and a weak acid. Strong base being sodium hydroxide and the weak acid being acetic acid or ethanoic acid. So the product that is formed is sodium acetate and water. So sodium acetate salt that is produced is a basic salt. That is why we observed the pH of sodium acetate solution is 8.5, which is a basic pH. Now let's move on to our next salt. Now we are going to prepare an aqueous solution of ammonium acetate. We have our ammonium acetate here. We can take a small sample of ammonium acetate into a test tube. We'll take a fresh test tube and we'll add a small amount of ammonium acetate to this test tube. And to this ammonium acetate that we have taken, we can actually add 5 milliliters of water. And before we add water, we can observe the nature of the ammonium acetate. Ammonium acetate is a white color crystalline solid which is soluble in water. While keeping that in mind, we can move on to taking 5 milliliters of water into our measuring cylinder. Now we can add the 5 milliliters of water into ammonium acetate and then mix it really well. As you can see, when you dissolve ammonium acetate in water, you produce a clear solution. And to this, we are going to be adding a few drops of our universal indicator. Keep in mind, students, we are going to be adding the same amount of universal indicator that we added to the previous test tubes as well. Now, students, as you can see, the color of the solution has changed. Let's compare it against our color chart here. Is it a light green like pH 7.5, or is it a yellow like pH 6.5, or is it pH 7? So, students, let's zoom in and very clearly observe the color change. So, we know it's somewhere between pH 6.5 to pH 7.5, but which color is it very clearly? You can observe it is not pH 6, you can observe it is not pH 7.5, it is pH 7. So, students, or it is somewhat close to pH 7 than it is to pH 7.5, or it is to pH 6.5. So, this solution has a pH value closer to pH 7. So, keep in mind, ammonium acetate has a pH value closer to pH 7. We can say the pH value according to what we observe here in the pH chart, the pH of this solution is pH 7. So, why does ammonium acetate have a pH that is close to pH 7? Ammonium acetate has a pH close to the pH 7. This is because this particular salt can be formed between the reaction of a weak acid and a weak base. If you take ethanoic acid or acetic acid, ethanoic acid is another name for acetic acid. So, if you take ethanoic acid and react it with ammonia, you will be forming ammonium acetate. So, ethanoic acid is a weak acid and ammonia is a weak base. So, when you react them together, the salt that is formed is going to be forming a neutral aqueous solution if both the acid and the base were equally weak. So, both ethanoic acid and ammonia were equally weak. Therefore, the resultant salt was forming an aqueous solution that is having a pH of pH 7, or in other words, the resultant salt was neutral, or in other words, an aqueous solution of the resultant salt is neutral. Now, let's move on to the next part of our experiment. Now, students, we are going to prepare a solution of zinc chloride. We have our zinc chloride solid here. We are going to take a small amount of zinc chloride into our test tube and add 5 milliliters of water to it. Let's take a small amount of zinc chloride and we are going to measure 5 milliliters of water into this measuring cylinder here. So, students, observe that zinc chloride is a white color solid, and we are going to add water to this zinc chloride solid that we have here. We have 5 milliliters of water. and we are going to dissolve this zinc chloride in our water that we have here. Students, as you can see, we were able to dissolve the zinc chloride and form a clear solution here. And now we are going to add the same amount of universal indicator to this test tube as well. We have made sure to keep the amount of universal indicator that we add to each test tube a constant. So we are going to be adding the same amount of universal indicator to this test tube as well. Now students, after mixing it, we can see the solution is not a red color. The universal indicator was red, but the solution's color is different, indicating we can use this color to observe the pH of the solution. So now students, when we are observing the color, please notice what color it is. It is somewhere between this particular color range. We will zoom into that color range. And let's observe, is it pH 7.5? It is a green color. It is not definitely pH 7.5. Is it pH 7? No, it is too light to be pH 7. And is it pH 6.5? So it is very close to pH 6.5. So if you are having any doubts, you can move on to pH 6 and observe whether it is close to pH 6 as well. It is closer to pH 6.5 than it is to pH 6. pH 6 is a bit of a brighter color than pH 6.5. So this color is a good match to the pH 6.5 color that we have here. So this particular solution has a pH of pH 6.5, which indicates that this is a slightly acidic solution. Now, let's move on to observing why that is. So students, when you take zinc chloride can be prepared by reacting zinc hydroxide with hydrochloric acid. Zinc hydroxide is not very soluble in water. It is slightly soluble in water, but it is not very soluble in water. So therefore, zinc hydroxide is not a very good electrolyte. Many of the ions that are in zinc hydroxide would not enter aqueous medium. So therefore, zinc hydroxide is not a very good or very strong base. So zinc hydroxide is a weak base. Then we react zinc hydroxide with hydrochloric acid, which is a well-known strong acid. When you react this weak base with a strong acid, the resultant salt will be acidic salt. The resultant salt is an acidic salt. So that is why we observed, when it comes to a solution of zinc chloride solution was acidic in nature. So now let's move on to the next step in our experiment. Now students, we have ammonium chloride here, and let's prepare a solution of ammonium chloride. We have our ammonium chloride solid. Let's take a metal spatula and a fresh test tube and add a small amount of ammonium chloride into our test tube. And then we can add 5 milliliters of water to this test tube. Before we add 5 milliliters of water, we can observe that ammonium chloride is a white color solid. And after that observation, we can move on to adding 5 milliliters of water. We have dissolved the ammonium chloride that we took into our test tube to form a clear ammonium chloride solution. Now let's add the same amount of universal indicator that we added to each of the previous test tubes. Now let's shake this to observe the color of the solution. The solution has turned into a different color. It is not red anymore. As we can see here, the universal indicator was red in color, but now there's a slight orange hue to our solution that we have here. So let's compare the color that was given off when we added universal indicator to our ammonium chloride solution. And let's find out the pH of our ammonium chloride solution here. So of course, students, this particular pH chart, we don't have to start all the way from the bottom because the colors at the bottom are blue. So since we know that this is not a blue color, we can start from somewhere around 7, pH 7. So I will zoom in on pH 7 values. Now you can see it is not pH 7. pH 7 is a green color, and pH 6.5 is a green mixed yellow color, and we have pH 6, which is a bright yellow color. But then again, we have pH 5.5, which is a very good match to this color, which is a slight orange color or light orange color. If you move on to pH 5, that is going to be a darker orange color. So we can observe that pH 5.5 is a good match for this particular color. So we now know the ammonium chloride solution that we prepared had a pH of pH 5.5. So pH 5.5 is an acidic pH. pH 5.5 is an acidic pH. So why does the pH of an ammonium chloride solution turn out to be 5.5? This is because ammonium chloride salt can be prepared when you react ammonia, which is a weak base, with a strong acid, hydrochloric acid. So when a reaction between a strong acid and a weak base produces a salt, the salt is going to have acidic properties. That is why when you have a reaction between strong acid hydrochloric and weak base ammonia, the resultant ammonium chloride salt had acidic properties. So an aqueous solution of ammonium chloride produced a acidic solution, and the pH of that particular solution that we prepared was 5.5, which is an acidic pH. Now let's move on to the next salt. Now we are going to take a look at a solution of aluminium chloride. To produce a solution of aluminium chloride, we have our aluminium chloride solid here. We can take a small amount of aluminium chloride into a test tube. And we are going to add 5 milliliters of water. So we can measure it with a measuring cylinder. And we are going to add our water to aluminium chloride here, and we are going to mix it really well. After mixing it really well, we produced a clear solution of aluminium chloride. And like in the previous steps that we have done before, we are going to add an equal amount of our universal indicator to this test tube as well. As you can see, when the universal indicator was added, the solution turned to a bit of a dark color. It is not a blue color, it is more towards the acidic side of the pH scale. So let's compare this color with our pH scale that we have here. It is definitely not a yellow color, it is more towards orange or red color. So let's observe whether it's close to pH 6. It is definitely not pH 6. Is it close to pH 5.5? It is not. Is it pH 5? It's very close to pH 5. Is it pH 4? So when you observe the color of the solution, it is quite close to this color, which is the pH 4. The pH is pH 4. Now students, when you are observing these colors, you have to make sure that you find the best fit. So this test tube, the solution in the test tube is quite close to pH 4 than pH 5. So the pH of this solution is closer to pH 4 than to pH 5. So we can say that the solution has a pH of 4, or the pH of this particular solution is 4. Now let's discuss why that is. Again, we can see the solution that we formed is a acidic salt. As you know, aluminium chloride can be produced by a reaction between aluminium hydroxide and hydrochloric acid. Aluminium hydroxide is not a very strong base, but hydrochloric acid is a strong acid. When a strong acid reacts with a weak base, the resultant salt is going to be a acidic salt. So therefore, that is the reason why aluminium chloride is an acidic salt. Keep in mind students, the pH of the aluminium chloride that we produced is pH 4 that we have here. So because of this, this particular aluminium chloride solution that we prepared has a very acidic pH, indicating that aluminium chloride aqueous solutions are acidic in nature. Now let's move on to our final salt. As our final salt, we have magnesium sulfate. This will be a good time to remind you of the solubilities of group 2 sulfates. What happens to the solubility of group 2 sulfate as you go down the group 2? Group 2 sulfates become less and less soluble. Magnesium sulfate is soluble, but as you go down towards barium sulfate, strontium sulfate, these are insoluble in water. So please remind yourself about these types of additional theory parts while watching these videos. Now let's take this test tube and add a small amount of magnesium sulfate. Now let's add a small amount of magnesium sulfate. As you can see here students, magnesium sulfate is a white color crystalline solid, and to this we are going to add 5 milliliters of water. We have taken 5 milliliters of water and we are going to add this water to our magnesium sulfate solid. Then we are going to dissolve the magnesium sulfate solid that we have taken into our test tube here. Now we have dissolved our magnesium sulfate solid here. To this, we are going to add our universal indicator, while keeping in mind that we added the same amount of universal indicator to each of these different solutions we prepared in the earlier instances. So the same amount of universal indicator is going to be added to this solution as well. Now students, we have formed a solution here, and let's observe the pH of this solution by comparing this color to our pH chart. So this pH seems to be close to pH 7. So let's zoom in to those colors. Is it pH 7.5? No. Is it pH 7? It looks like it is very clearly pH 7, but let's compare it to pH 6.5 as well. Is it pH 6.5? Is it pH 6? Certainly not. So it is very close to pH 7. It is very close to pH 7. This indicates the magnesium sulfate aqueous solution has a pH of pH 7. So students, we observed when it comes to magnesium sulfate, the pH of magnesium sulfate was 7. So therefore, it is a neutral salt, or the pH of an aqueous solution of magnesium sulfate will be neutral. Magnesium hydroxide, when reacted with sulfuric acid, can produce magnesium sulfate. So this is a reaction between a strong base and a strong acid. Therefore, the salt that is produced was also a neutral salt, or the salt that is produced will have a neutral pH. Students, as an additional reaction, we can take a small amount of strong acid such as sulfuric acid and add our universal indicator to our sulfuric acid solution and observe what the pH of sulfuric acid is. Let's take a small amount of sulfuric acid into our test tube here. And let's proceed to add a small amount of pH indicator as well. We can see upon addition of the indicator, it immediately started changing color to a very strong red color. So this is a very strong red color. So students, upon the addition of a few drops of universal indicator to our sulfuric acid, we can observe that it turns to a bright red color. That particular bright red color is nowhere to be seen in this color chart. That is because the universal indicator that we have here gives us a color chart for pH values ranging from pH 4 all the way up to pH 10, actually pH 11, all the way up to pH 11. So it goes from pH 4 all the way up to pH 11, but it does not give us the color of solutions that are formed with lower pH values like pH 3 or pH 2. So because of that, we can be very certain this particular red color is corresponding to a lower pH than pH 4. So sulfuric acid is quite a lot more acidic. pH of sulfuric acid solution that we have here is not going to be 4, it is a lower pH value than pH 4. Unfortunately, since this particular color chart does not include the color of pH values that are lower than pH 4, we can't be sure exactly what pH value this sulfuric acid is at. However, we can be certain that the pH value of sulfuric acid is lower than pH 4. Now, let's take another test tube and add a small amount of sodium hydroxide. This is concentrated sodium hydroxide, so let's dilute it a little further by adding water. We have diluted the sodium hydroxide. We have taken concentrated sodium hydroxide and now diluted it a bit further. To that, let's add a small amount of our universal indicator. As you can see, when the universal indicator is added, the color started changing immediately. And the color that is observed here is a dark purple color. So let's compare the color that we have observed here with the color chart here, and you will be noticing that this purple color that we see here is nowhere to be seen in this color chart. That is because, students, the sodium hydroxide solution is more basic than the pH values that are indicated in this particular color chart. So the highest pH value that this color chart indicates is pH 11, but the sodium hydroxide solution that we have here might have a higher pH value than pH 11. Because of that, the color that is produced here is not observed in this color chart that we have here. So now it is very clear, when there is a very strong acid, we can observe a very clear red color in our universal indicator solution, and if you have a very strong base, the color is going to be a strong blue purple color. With that, we can now move on to our summary. Students, let's take a look at the summary of our experiment number 35. In this experiment, we wanted to observe the pH of different aqueous salt solutions. So we took small solid samples of different salts and dissolved each of these salts in 5 cubic centimeters of water to prepare their aqueous salt solutions. Afterwards, we added a few drops of universal indicator, and we made sure to add the same amount of universal indicator to each of these solutions. When we add universal indicator to a solution, the solution will change its color due to the presence of the universal indicator. So using the color that is seen in the solution after the addition of universal indicator, we can determine the pH of the solution. Usually, when you purchase a universal indicator reagent bottle, it will come with a color chart. So we have that color chart here. We compared the colors of each of the different solutions that we have here with this color chart, and then obtained the pH value of each of these solutions. We initially added a few drops of universal indicator to water. The water turned to a greenish solution. due to the presence of universal indicator, now the water has turned to a greenish color. You can compare this color against the color chart of the universal indicator, and when we did that, we observed that the pH of water was pH 7. pH 7 is the neutral pH at this room temperature. So the water that we have has a neutral pH. Then we moved on to sodium chloride. So you can see the sodium chloride, when added with our universal indicator, turned to a greenish color. After comparing this color against our color chart, we found out the pH of sodium chloride aqueous solution is also 7, indicating that sodium chloride solutions are also neutral according to their pH. So sodium chloride aqueous solutions are neutral solutions. Then we took an aqueous solution of sodium acetate. Sodium acetate, when added with universal indicator, turned to a darker green color. And when we compared this dark green color against our color chart, we found out that the pH of this solution is 8.5. The pH of this solution is 8.5. This indicates that sodium acetate aqueous solutions are basic or alkaline in nature. This is due to the fact that sodium acetate can be formed when a strong base is reacted with a weak acid. Strong base sodium hydroxide, when reacted with acetic acid, you form sodium acetate. So the salt that is formed has basic properties. Then we took ammonium acetate. Ammonium acetate, when added with universal indicator, turned to a greenish color yet again. And when we compare this color with the universal indicator color chart that is provided to us, we found out the pH of the ammonium acetate solution is 7. This indicates that the ammonium acetate solution had a neutral pH. Then we moved on to zinc chloride. Zinc chloride, when added with universal indicator, produced a yellow color. And when we compared this yellow color against our color chart, we observed that the pH of the zinc chloride aqueous solution was 6.5, indicating that zinc chloride solution was an acidic solution. So zinc chloride is an acidic solution with a pH of 6.5. Then we move on to ammonium chloride. We can see here, when we take small amount of ammonium chloride and when we add a pH indicator, universal indicator to it, the ammonium chloride aqueous solution turned to a bit of an orange color. And when we compared this orange color against the color chart that we have here, we noticed the pH of this ammonium chloride solution is 5.5 or close to 5.5 in pH. So this indicates that ammonium chloride is acidic. Ammonium chloride is acidic. Then we moved on to aluminium chloride. Aluminium chloride, when added with universal indicator, produced a red color. This red color, when compared against our color chart, indicated that the pH of aluminium chloride aqueous solution is 4. So pH 4 is an acidic pH. It's a bit of a strong acidic pH, indicating that aluminium chloride is somewhat more acidic than all the other acidic solutions that we have here. Aluminium chloride is a acidic solution. And finally, we moved on to magnesium sulfate. When we dissolved magnesium sulfate in water and when we added universal indicator to it, we observed the color that is produced was a green color. And when we compare this green color against our color chart, we notice the pH of magnesium sulfate is 7. So pH 7 is a neutral pH. So magnesium sulfate aqueous solutions are neutral solutions. With that, students, we observed how different aqueous solutions can be acidic, basic, or neutral. Students, with that, we have concluded our experiment 35. In experiment 35, we observed how different solutions can have different pH values, and based on their pH values, how we can determine whether they are acidic, basic, or neutral. So now, let's move on to our studio again to discuss more theory parts and questions revolving around this experiment.